Hello everyone, in this video we're solving a problem 3.159. We're going to apply the linear impulse linear momentum equation in this problem. So let us read it together. So the statement here is referring to a previous problem, but we really do not need to do that. We can solve this problem independently. So the force P is held at a constant 30-degree angle relative to the horizontal, and P is a function of time. So that's the scalar P. It has a linear portion, 50t, equal to 50t for t between 0 and 3 seconds, and 0 for t greater than or equal to 3 seconds. Okay, so P is given as a function of time, and it's making a 30-degree angle with the horizontal. So if I draw the free body diagram of the block, I need to choose my basis. P here has magnitude scalar P that's changing in time, and it's making a cosine 30-degree angle with the horizontal. So its direction is cosine 30x plus sine 30 EY. Great. What other forces are acting on the block? The weight, the normal, and the friction force. Weight minus mgEy. The normal force is NEY. And notice that the normal force is going to be a function of time. It's going to depend on P, right? So P has a vertical component, so it's going to affect the normal force. And then the friction force. Well. Is the friction force static or kinetic? We need to know so that we can to know if we can prescribe it or if we need to solve for it. Let us see. So the problem says that, determine the time Ts at which the initially stationary 20 kilogram block. Okay, great. The block is initially stationary, so initially the friction is static. Is it going to remain that way? Apparently not, because they're asking for the time Ts at which the initially stationary 20 kilogram block comes to rest again. So it probably will move and then it will come to rest again. Okay, so this is what's happening. Initially the block is at rest. So from 0 to some time t1, I'll call it, the block is at rest, so friction is static. Okay, static friction, meaning that its expression is, it's basically unknown. We can assume that it has some direction, some value along minus Ex. I'm putting minus Ex just because I drew it to the left like this, but really we will solve for this scalar ff, and if it's positive, it's positive, and if it's negative, you have to flip the direction, kind of basically. It corrects itself. And then, okay, so we have initially a static block with no force applied on it. Then we apply a force P to it, and P is gonna increase. It's increasing as a function of time until it stops. So I think what's happening is that P increases as a function of time until a certain time instant where the block starts to move. So from T1 to T to whatever, some other instant, the block is gonna move, right? T1 is when the block initially slips. And Ts is when the block comes to rest again. Why will the block come to rest again? Well, because basically force P is going to be applied to it. It's going to accelerate it until at t equals to 3 seconds, force P is removed. Then the block is going to start decelerating because of friction. So friction is still going to be kinetic, but it's going to decelerate the block. There's no force P that's pushing the block forward. So the block is going to decelerate until it stops. So in that transition, when the block is accelerating, then decelerating, it is moving, friction is going to be kinetic. And its expression is totally known, minus mu k n Ex, right? Because the block is going to slip along Ex, so the friction force is going to be opposite to that. The surface is stationary here. Okay, great. So we want to determine T2. T2, we need to find U. Okay, so P is given as a function of time. this is our balance law basically. F equals ma, but p is given as a function of time. We're probably gonna then use the integral form of that. So the linear impulse, linear momentum equation. The integral of f dt is equal to g at the initial time minus g at the final time. Okay, so let us see. Should we integrate between T0 and T1, 0 and Ts, T1 and Ts? Well, if I integrate between 0 and Ts, I know that g at Ts is what? G at Ts is, well, Ts is when the block comes to rest again, so g, which is mv, at Ts is going to be equal to 0. And g is initially 0 because the block starts from rest. Okay, that's fine. The integral of f dt from 0 to Ts is 0. Oops, what did I do? Undo. Okay. Now, if I integrate between T1 and Ts, what will happen? Okay, g at Ts is still 0, but what is g at T1? T1 is the time at which the block is about to slip. Slip is gonna initiate, so the velocity is still 0 at T1, so I can even write that g at T1 is 0, or very close to 0. So I do not have to integrate f between 0 and Ts. I can integrate f between T1 and Ts, and that would be equal to 0. Okay, cool. So then I need to find T1. I think I can find T1. T1 the time at which we start slipping. Well, we know that friction is static when it satisfies the static friction criterion. Ff is less than mu Sn. Here we have sticking. Okay, when does slipping happen? Initiates, or about to initiate, when this criterion is not satisfied. So when the magnitude of the friction force becomes equal to mu Sn. Okay, let us see. Let us write F equals ma. In this situation, F is 50, P, which is 50t. So I'm assuming that the time T1 at which slips initiate is between 0 and 3 seconds, which physically makes sense. If the block is gonna slip, it's gonna slip when P is applied to it. And then we will solve for T and we'll double check, make sure that it says T1 is in this interval. Okay, so solving F equals ma, I get 50t cosine 30 degrees Ex plus sine 30 degrees Ey minus mg Ey plus Ney plus the friction force in this interval. Well, what is Na? A is 0 because friction is still static. I haven't moved yet. I'm looking for the instant at which I'm about to slip, but I haven't slipped yet. I can project this equation along Ex and Ey. Ey gets me the normal force, mg minus 50t sine 30 degrees. So the normal force is decreasing, right, in time. And then the friction force is equal to 50t cosine 30 degrees. So I can solve for the time where the friction force is equal to mu Sn. So 50 t cosine 30 degrees, that's T1 at which we start slipping, is equal to mu S mg minus 50t sine 30 degrees, T1. And we can solve for T1. And we need to double check again that T1 is between 0 and 3 seconds. Okay, so this is how we solve for T1. Now that we have T1, we go back to this integral, the integral of f dt between T1 and Ts. So what is f? T1 we found, Ts is what we need to find. F is the sum of all the forces, that's P plus W plus N plus the friction force dt is equal to 0. And I think we can double check this, but, or shall we? Shall we project now or shall we project later? I'm not sure. Let's keep that for later. Okay. Now I'm gonna integrate P between T1 and Ts. Now P, the expression of P changes. P basically disappears for times less than or greater than 3 seconds. So P, that just is non-zero between T1 and 3. And that would be equal to 50t cosine 30 degrees Ex plus sine 30 degrees Ey. Okay, dt. Now the weight. The weight is constant. T1 to Ts minus mg Ey. Okay, dt. And then the normal force, right, you see here, it depends on P. So I need to split the integral between T1 and 3. N is equal to mg minus 50t sine 30 degrees Ey dt plus the integral from 3 to T2, and that's just mg dt. The P is gonna be 0. Okay, mg Ey dt. Okay, and then the friction force. The friction force from T1 to 3, well, from T1 to Ts, friction force is now kinetic because we're gonna start slipping. So it's equal to minus mu k n. N depends on P. P depends, or P is discontinuous, so I have to split this integral again. Yeah, I do. T1 to 3 minus mu k n mg minus 50t sine 30 degrees Ex dt plus the integral from 3 to Ts of minus mu k, now just mg Ex dt, and this should be equal to 0 vector. Okay, let us see. Interesting, quite long though, but interesting integral, interesting equation. Let me try that again. Okay, bravo. So let us see here. What are my unknowns? T1 is known, 3 is known, 50t, I can integrate these equations. Ts is basically my unknown here. Right, so I can basically just project along Ex. I'll get a scalar equation and then I can solve that for Ts. So for example, I'll get integral from T1, I've already solved for T1, the integral from T1 to 3 of 50t cosine 30 degrees dt. Weight goes away, normal force goes away, these are both along Ey, and then minus T1 to 3 mu k mg minus 50t sine 30 degrees dt minus mu k mg dt from 3 to Ts is equal to 0. Okay, so that should be easy to integrate, right? 50t squared over 2 cosine 30 degrees evaluated between T1 and 3 minus mu k mgt minus 50t squared over 2 sine 30 degrees evaluated between T1 and 3 minus mu k mgt between 3 and Ts equals to 0. Okay, 25t squared, well, 25, 3 squared minus T1 squared cosine 30 degrees minus mu k mg 3 minus T1 minus 25 3 squared minus t1 squared sine 30 degrees minus mu k mg ts minus 3 is equal to 0. And this equation is quadratic. No, it's not quadratic. It's linear in t1, so we can just solve for our unknown ts, and that's it. T1 is already known. Okay, that's great then. That's it for this problem.